Okay, hearing no questions, let me go ahead and um, introduce Rob. Rob is Chief Platform Architect of NVIDIA's data center products, and we all extensively collaborate with Rob. Rob works with the global hyperscale data centers in terms of his influence around AI technology for future NVIDIA products and roadmaps. Rob has an extensive background in processor and system architecture, multiple patents, and is an expert in AI and data center hardware. So with that, let me pass it on to Rob to take it away.
Thanks. Thanks very much. So I'm going to start with a slide, which is, you've basically already seen this a few times already. This is a slightly older slide from NVIDIA. This is our view of how things were evolving, a little over a year ago. Very similar message, except, we tend to use CEO math. So the complexity and compute resources that are being consumed by AI, leading edge AI, is growing about 10x per year. So really easy number to remember. That ends up, it means it's doubling every few months. And the reason this is happening is because it works so very well. So the models get bigger, the data gets bigger, the data sets get bigger. And so, the consumption is growing, an order of magnitude a year. So in response to that, we do in fact have a very rapid hardware evolution. We do take advantage of silicon advances. We are constantly working on software optimizations. But even so, we can offer sort of on the order of 3x year-on-year improvements through those mechanisms, which is actually pretty astonishing when you step back and think about it. But in order to accommodate 10x year-on-year, we're seeing it's very interesting, the CAGR that Bharath showed. So my trajectory shows about 3.5x year-on-year cluster growth size. So very similar number. So this is in effect the problem statement of AI. As much as we're doing, as compelling and awesome a job as we're doing to make the AI throughput more efficient and better, it's still not nearly enough. So I also wanted to take a few cartoony slides here and try to help you see some of the problem as well. This was prepared for a DARPA workshop about a year ago. And because of the position in the ecosystem, I managed to talk to all of the hyperscales and an awful lot of researchers in the world, and get some anecdotal information about what the common, training size is, how, what the clusters look like, what they're doing. And I happen to keep track of that over time. And this is sort of anecdotally the way it's looking. And you can see the green bars are sort of the common GPU count in a single run for AI training. And you can see that going up over time. And in fact, one of the A100 platform, which I'll show you later, has been incredibly popular for scale, cluster training in the cloud. And one of the cloud vendors has told me their most common, their average single training run size is 512 GPUs. So that's not the biggest. They're certainly getting well over 1,000. That is their average single run training size. So we're seeing that progression of cluster size just compounding really rapidly. We're in talks with people deploying 2,000, 4,000 GPUs for single training runs. And if you look at that, that's sort of on the order of, megawatts per training run. So it's a big problem. And then I want to also mention that it's a bit counterintuitive, but because of the heartbeat of these neural networks, they, as Bharath talked about, there are different roof lines that we hit into, and every different neural network has a different heartbeat in this, and you will hit compute roof lines, memory bandwidth roof lines, and communication roof lines. And you cycle through those, and the transition between some of those has some very rapid current changes. And over time, the transient power as a percent of the TDP power has been increasing over time. Now, I want to say this is very useful. It's valuable. An incredible amount of work gets done in this time period. But if you're talking about a microsecond transient, that's going to be absorbed by the device and the peripheral logic and the board level. But if you're talking about milliseconds or tens of milliseconds, which is really what's going on, that rolls back into the infrastructure and the power supplies, the racks, the rows. And if you start thinking about an average or typical run being 512 GPUs, you've actually got a row of compute infrastructure that is running synchronous, highly aligned, and these transients are massive. So logically and algorithmically, we're doing things to reduce those transients aggressively. But there is value to them. And I just want to point that out, that in fact, it is more efficient to let those transient happen. It's just very hostile to the data center. And another cartoon, Broth sort of touched on this as well, is that if you take the current trends, and we're not seeing a slowdown, if you take the current trends, we're talking about, 1,000 megawatt training run in a few years, so gigawatts. And that's just, it's hard to believe that's sustainable. Nonetheless, that's the direction we're going. And then the interesting thing is when I do talk to some researchers, they're like, no, 40,000 GPUs for a single run will be sufficient. So even the people who are fairly sanguine think it's an incredible number of GPUs that will be involved in a single training run. So again, this sets the problem statement. I wanted to take a second, mostly just because this is kind of cool, to help you visualize what these look like. So on the top right is an A100 GPU. It's a full reticle, or essentially a full reticle 7 nanometer FinFET device. In the real device would have stacks of HBM down either side. And at the bottom right is an HGX board. This is called the Delta board. And if you buy systems, or if you go to, for example, Azure or Google Cloud or AWS or Oracle Cloud, this is what you'll be using, this board exactly. There are 6 of the GPUs with heat sinks. 2 are shown bare. So 8 A100 GPUs total. Those are 400 watts each. And in the back row with the heat pipes are NV switches. Those are incredibly high bandwidth interconnect, NVLink interconnect between the GPUs. It's about 2.5 terabytes per second, not terabits, terabytes per second between the GPUs. And then out the back, the connectors are NV links that can exit the board, same bandwidth. So we have full bisectional bandwidth exiting the board that can be connected to other systems. On the bottom right, or sorry, on the bottom left is the PCI interface to the host nodes. This is a very heavy board. It consumes a lot of power, but it does very efficient compute. And if you look at the left is a diagram of the sort of canonical reference architecture for a system built like this. And the board on the right is just the green boxes labeled GPU, and below it, the NV switches. So it's also connected to a PCIe switch plane with NICs and local storage, and then high-end dual socket CPU. And what we found ourselves going from a gaming card company to an HPC cluster company. So this is Selene. It's our 4th generation reference design Superpod. And we've ended up having to do this both for our own internal research and development and software development and tuning, but also because our customers are demanding it. The clusters are becoming so complex that they want a reference design that's efficient and high powered that they can rely on, they can drop software on and predict their performance. So this is the #1 ML perf benchmark machine that's commercially available. It's the #6 on the top 500. So it's the most powerful privately owned supercomputer in the world. And depending on the configuration, it's #2 to #10 on the Green 500. Half a year ago, it was #1. So in spite of the power this Superpod consumes, it's literally about the most efficient way you can do complex computing on the planet. And front elevation, so you get an idea. This is what we call a scalable unit. It's 20 nodes that you saw the picture of. And then we take 7 of these scalable units that include the compute, the power, networking, and storage. We combine them and you get 1,120 GPUs with a fully connected fabric. And then we can stitch 4 of those together to easily get to a 4,000 GPU pod. And then those 4,000 units can be started to stitch back to back to get 8,000 or more GPUs in a pod. And this is a boilerplate design today. For example, Microsoft Azure is a logical clone. It is an exact copy of the Superpod architecture. With that, I kind of want to give you guys some key takeaways. I think really the challenge, the problem statement is that AI is consuming resources at about a 10x per year rate. It is unbelievable, but we're not seeing a slowdown. If anything, we're seeing an increase in that growth rate. And also, as Bharat pointed out, every neural network is different. The state of the art changes every 6 months. Each new neural network architecture has very, very different metrics. Some are compute heavy, some are communication heavy, some are memory heavy. And some are all of those, but at different points in the training run, they hit a limit on each of those. So flexible platforms are needed, as appealing as it is to optimize hardware around these problems. I don't think we're there in the evolution of AI yet. It is changing still so unbelievably rapidly. Cluster scales, it's now really common to have hundreds or thousands of synchronous GPUs operating at once on a single problem. That number is likely to grow even as the capability and power dissipation of those GPUs continues to grow. And it's, optimizing throughput per watt or throughput per dollar or throughput per system. It's not just teraflops. It really is both bandwidth and latency for networks and memories. It can be memory capacity, and as well at times it's teraflops. And again, there's real value that you can extract from those difficult power transients. You actually get overall a more efficient throughput, but it is a real challenge for infrastructure and power provisioning to accommodate those things. So I think that's it for me. I don't know if we have time for questions or not.
We do, Rob, for a question. I think I will maybe look back at the one that we had earlier for Catherine, and I think you may be able to take a crack at it from an AI context. In current state-of-the-art data centers, how do you look at energy consumed by compute memory versus rest of the cluster, and how do you see this changing going forward?
No, that is a great question. I would say traditionally, it's been a fairly stable ratio between CPU cores and network bandwidth, so it's been fairly constant. What we're finding is, as clusters grow, it's no big surprise that the cross-sectional bandwidth that's required also grows super linearly, and we're very quickly seeing the fabric be a major contributor to the overall power consumption, and that is very concerning. And so, we ourselves are trying to do a few things to minimize the amount of energy going into the communication, both algorithmically and physically. But it is not enough, and there are tremendous opportunities there. One of the biggest issues is we cannot compromise latency. Latency is very critical. So I think as a percentage, it is growing pretty aggressively.
Bharath, there's also a question in the Q&A section. I can read it if you can't see it right now.
Go ahead, Mark.
So the question is around how you talked about 10x power growth rate, and how is that divided on the training side versus the inference side?
So it's not entirely the same, but we are definitely seeing the same trend on inference. Like we've got a couple of customers who are we've gotten used to talking about very small devices for inference, especially with embedded, our mobile phones can do things, automotive applications. But the reality is some of these neural networks are so immense that we have several customers who are actually using the full DGX system I showed, that full huge board. That is a single inference machine, one inference, one at a time. Obviously we're working to try to optimize that. But I think that's the long-term trend, is that inference is also going to have a lot of complexity and capability consumption. And not to mention the sheer number of inferences that happen. It is a brutal workload, I think, on data centers.
I see John has his hands up.
Well, is there any water cooling? I mean, getting 4 kilowatts off a board is pretty impressive. When does water cooling become necessary?
When we can't do air cooling anymore. I think conceptually everybody loves liquid cooling. Immersion cooling is really awesome. They're just really awkward to deploy in the data center, and as a result, everybody's preferring to avoid it as long as possible. But yeah, I think we're right on the cusp. We were expecting our next generation to require liquid cooling. I think we've dodged that bullet for the moment, but there are a lot of data centers that simply can't accommodate this kind of cooling, and they will migrate to liquid or immersion. We have we're getting some fantastic experience with immersion as well. It's a great way to cool. It's incredibly awkward to build a data center for it.
Thanks.
Dodging the bullet sounds like the right word.
Yeah. Yes. Yeah.
That certainly sounds like the right word. Thank you, Rob. And I think Rob will be back for the panel. So please continue to file away your questions, and we'll see if Rob will answer them later on.